Hi, this is Alex from devstories.eu. Biopython Fundamentals, Episode 1 of 18. Treating a DNA sequence as a standard text string works fine until you need its opposite strand. Simple string manipulation in Python falls apart when you realize biological transcription is not just about replacing letters, but about directionality and distinct genetic codes. This is exactly why we use Introduction to Biopython and the Seq object. At its core, a biological sequence is a string of letters representing molecules like DNA, RNA, or proteins. In Biopython, the central data structure is the Seq object. It wraps standard Python string behavior but attaches biological awareness directly to the data. Because it behaves like a normal string, you can do everything you normally do with text. You can check the length of a sequence, you can count how many times a specific pattern appears, you can slice it to extract a smaller piece. When you slice a Seq object, the result is not a standard text string, it is a new Seq object. This ensures you never accidentally strip away the biological methods when you parse a sequence into smaller fragments. This is the part that matters. Standard strings do not understand biology. DNA is double-stranded and sequences are read in a specific direction. If you have a sequence of coding DNA and you need the opposite strand, a simple reversal is biologically incorrect. You must reverse the order of the letters and swap each base for its structural pair. The Seq object handles this with a single reverse complement method, returning a biologically accurate opposite strand. Beyond structure, the Seq object handles the central dogma of molecular biology directly. Consider a short coding DNA sequence. To convert this into messenger RNA, you call the transcribe method on your sequence. Under the hood, this handles the specific letter substitutions, replacing thymine with uracil, and gives you back an RNA sequence. If you start with RNA and need the DNA equivalent, a back transcribe method reverses that process. Once you have your sequence ready, you generally want the resulting protein. You call the translate method. This automatically groups the sequence letters into triplets, evaluates them as codons, and returns a new Seq object containing the amino acid sequence. Biology is rarely uniform, and the standard genetic code does not apply everywhere. Organisms, like certain bacteria, or organelles like vertebrate mitochondria, read codons differently. The translation method accounts for this through translation tables. Instead of writing custom logic for a mitochondrial sequence, you simply pass the translation table argument to the method. You can provide the official NCBI table number, such as Table 2 for vertebrate mitochondria, or the table name as text. The Seq object recalculates the amino acids using those specific organism rules. The true power of the Seq object is that it prevents you from writing brittle, error-prone text parsing functions for established biological processes. If you want to help support the show, you can search for DevStoriesEU on Patreon. That is all for this one. Thanks for listening and keep building.